Hi everyone. So today here we have gathered two grade 9 students. They took on the challenge of understanding projective geometry and they've used it in 3D reconstruction. So why don't you guys introduce yourself and then start with the presentation? Siddharth, Adwita, so one of you.
Hello, my name is Siddharth Garimella, and I'm a grade 9 student at the Webb Schools in California.
Hi, I'm Adwita, and I'm in grade 9 in Ghana International School. And yeah, I'm excited to be here.
Okay, so one of you start with the proceedings and then tell when do you want to change the slides, okay?
Siddharth, would you like to start?
Yep. So, as Shai sir mentioned, our project is an introduction to projective geometry and its applications in 3D reconstruction. Could you change the slide, please? Okay, so as a brief overview, so projective geometry can provide a mathematical framework transformations and projections, and we can see applications of this in 3D modeling, computer vision, etc. So with this project, what we were trying to achieve was we were trying to achieve almost 3D reconstruction through depth estimation, and we did this using projective geometry and concepts in projective geometry like homogeneous coordinates, epipolar geometry, and cross ratios. And the findings show that there is potential for future research to future enhance depth estimation accuracy to improve 3D reconstruction. Next slide.
So
Oh yeah.
do you want to go or?
No, you can present this slide.
So this is an overview on projective geometry. So it studies properties of geometric figures invariant under projective transformations. The key concepts are homogeneous coordinates, epipolar constraints for stereo vision, and triangulation for depth computation. And it also includes the applications in computer vision and 3D modeling. You can go to the next slide, please. So the definition of a projective space. So let V be a vector space over a field F. The projective space PV is the set of all one-dimensional subspaces of V. If the dimension of V is n plus 1, then the dimension of P of V is n. Examples, dimension V is equal to 2, then P of V is a projective line. Dimension V equals 3, then P of V is a projective plane. Elements of E of V is one-dimensional subspaces of V are referred to as points of the projective space. Next slide, please. Do you want to present the slide or? Okay. So representation of points in projective space. So given V in V, not including 0, we write V is equal to span of V to represent the one-dimensional subspace spanned by V. Here, as you can see on the slide, it represents a point in PV, and then V is a representative vector for this point. Next slide, please. So these are just the respective examples of projective subspaces. So for example, the dimension of P of U is equal to 1. That's a projective line. Dimension of P of U is equal to 2, and that is known as the projective plane. And the dimension of P of U equals to n minus 1 is known as the projective hyperplane. So in contexts where the term projective is evident, it may be omitted for brevity. Next slide, please. Now we go on to properties of projective subspaces. So operations include intersection. So as you can see, P of U1 intersect P of U2 is equal to P of the intersection of U1 and U2. Now there's another one, span, which is also known as join. It says P of U1 union P of U2 is equal to P of U1 plus U2. Unlike Euclidean geometry, there is no concept of parallel lines in projective geometry. Next slide, please. So key propositions. So the first proposition is through any two distinct points in a projective space, there exists a unique projective line. The second proposition is any two distinct lines in a projective plane intersect at exactly one point. Next slide, please. So proof techniques. So proofs for these propositions are effectively approached using linear algebra, and we can form even more general statements using like broader frameworks. You can go on to the next slide.
Yep, so projective subspaces. So I know we've discussed this already a little bit, but just as a brief overview of what they are. So projective subspace of the projective space PV is defined as a projective space PU, where U is a vector subspace of V, which follows the following statement. And if the dimension of P of U is K, then K plus 1 is the dimension of U, and P of U is referred to as the K-plane of P of V. Next slide, please. Okay, so here, homogeneous and affine coordinates. So homogeneous coordinates can provide a representation of coordinates which is invariant under scaling, and 2D data can be transformed to 3D using linear transformations. An affine coordinate system on a plane is defined as an ordered pair of non-collinear vectors. Okay, so projective transformations and PGL groups. So a map of P W is defined as a projective transformation if there exists an invertible linear map F, which is V to W, such that F of V is equal to capital F of V for all V in P of V. And a projective linear group, or a PGL, are a group of transformations of projective spaces, and projective transformation map lines and lines to lines, and more generally, K-planes to K-planes. Next slide, please.
The 3D reconstruction model. So the first is depth estimation using projective geometry. So the key steps include perspective projection modeling, camera calibration, using intrinsic and extrinsic parameters. Number 3, epipolar geometry constraints, and 4, triangulation for depth computation. Next slide, please. So models of real projective spaces. So every point in the real projective space, Rp to the power n, corresponds to a one-dimensional subspace U in R to the power n plus 1, generated by a non-zero vector V in U with V not equal to 0. So using the Euclidean norm in R to the power n plus 1, representative vectors can be chosen with unit length, placing them on the unit sphere S to the power n in R to the power n plus 1. Opposite points V and negative V on S to the power n are equivalent, leading to the construction of Rp to the power n as shown. Next slide, please. Alternative representation of Rp to the power n. Consider the upper hemisphere of S to the power n, where opposite points along the equator are merged. The open hemisphere is homeomorphic to R to the power n, serving as a projection from the origin onto the tangent plane at the North Pole. The equator forms the sphere S to the power n minus 1. Next slide, please. Do you want to go, or?
Oh, no, you can go.
All right, so real projective spaces, the example. So Rp to the power 0, an example of this is the real line R to the power 1. It has only one dimensional subspace, making Rp to the power 0 a single point. Rp to the power 1 has the following example. So points of Rp to the power 1 are one-dimensional subspaces of R to the power 2, represented as x1, as shown, with x2 not equal to 0. Using affine coordinates x1, x2 in R, p to the power 1 is equivalent to the real line plus a point at infinity. This representation forms a circle with an additional point at infinity. So now, moving on to rp to the power 2. Points of rp to the power 2 are one-dimensional subspaces of r to the power 3, represented as shown with x3 not equal to 0. Affine coordinates u1 equals x1, x3, and u2 equals x2, x3 provide a representation of rp to the power 2 as r squared plus the projective line at infinity. You can move on to the next slide. Okay, so the complex projective line. The complex projective line Cp to the power 1 is the union of the complex plane C and a point at infinity. In complex analysis, this structure is called the Riemann sphere, denoted as shown, and it provides a way to extend C into a compact form suitable for projective analysis. The next slide, please. Perspective projection and 3D reconstruction. So what is perspective projection? So it stimulates how the human eye perceives depth, converting 3D points into a 2D image plane. It follows the pinhole camera model, where rays from a 3D point converge through a single point camera center onto a 2D plane. You can move on to the next slide. So the mathematical model is shown here, where K represents the intrinsic matrix or camera properties, and R, T represents the extrinsic matrix known as the camera position and orientation. Next slide. Okay, so the role of perspective projection in 3D reconstruction. So the first role is projection. So it maps 3D points onto a 2D image plane. And the second one is depth estimation. So algorithms like Midas calculate relative depth values. 3D reconstruction. It combines depth data and camera parameters for 3D modeling. Next slide. Okay, so.
Yep. So here's the application in the 3D reconstruction project. So the applications in the project would be reconstructing monuments such as the Eiffel Tower and the Sphinx using depth maps, point clouds, and 3D models. And we utilized perspective projection to transform 2D images to 3D representations. Next slide, please. Okay, so camera calibration. So the purpose of this was to compute intrinsic and extrinsic parameters for accurate 3D reconstruction. So the intrinsic parameters are described by the matrix K, which is shown down here, where fx and fy are the focal lengths, cx and cy are the principal point coordinates, and s is the skew coefficient. The extrinsic parameters combine rotation r and translation t, as shown below. Next slide, please. Okay, cross ratios. So let P1, P2, P3, and P4 be 4 distinct points on the projective line RP1 or CP1 with homogeneous coordinates PI, which is XI and YI. The cross ratios of these points is defined as shown, where VI of XY and YI are representative vectors of the points PI. Next slide.
Okay, so depth estimation overview using projective geometry. So depth estimation in an image aims to determine the distances of objects from the camera, effectively reconstructing a 3-dimensional scene from its 2-dimensional projection. Projective geometry provides a mathematical foundation to model how 3D points in the scene are projected onto their corresponding 2D points on the image plane. Fundamental concepts of projective geometry, such as homogeneous coordinates and transformations, are key to accurately modeling this process. Next slide, please.
Okay.
Okay, you can go.
Here's the role of epipolar geometry. So in stereo vision, where a pair of images is captured by cameras with known relative positions, projective geometry describes the epipolar constraint that relates to the points P and P dash of the two images. The constraint is represented by the fundamental matrix F, as shown below. By utilizing this constraint, any point in the first image can be mapped to a corresponding point in the second image if it lies along the epipolar line. This is crucial for estimating the depth of the corresponding 3D point. Using this, we can estimate depth in like the 3D model. Next slide, please. Okay, so this is depth estimation using cross ratios. So the cross ratio is a projective invariant that relates to four collinear points, as I said before. So given four distinct points, P1, P2, P3, and P4 in a 3D scene, their projections on the image plane form a corresponding cross ratio that remains invariant under projected transformations, and that cross ratio can be seen below, whereas cross ratio of P1, P2, P3, and P4 would be x1 minus x2 times x3 minus x4 divided by x2 minus x3 times x4 minus x1. Next slide. Okay, so this is more into depth estimation using cross ratios. So I think, yeah, most of this is already covered already. So you can go to the next slide.
Okay, so triangulation for depth calculation. So triangulation, it was one of the methods mentioned earlier, but it's more in depth here. So triangulation computes the 3D coordinates p equals to x comma y comma z to the power t by intersecting back projected rays from multiple cameras. Using known intrinsic and extrinsic camera parameters, triangulation ensures accurate depth estimation for corresponding points. Next slide, please. Okay, so building the depth map. So first, you have to detect and match key points across multiple views using algorithms like SIFT or SURF. Apply the epipolar constraint to narrow down correspondence search. 3, compute cross ratios to impose additional geometric constraints on depth consistency. And 4, perform triangulation to determine 3D coordinates of matched key points. And the 5th step is to generate a depth map where each pixel's intensity represents its relative distance from the camera. You can go on to the next slide. Okay, so this is the mathematical framework for depth estimation. So for two cameras with projection matrices P and P, and P apostrophe and corresponding points P and P apostrophe. So it's shown here below. So depth C is computed by solving these equations, and the cross ratios and triangulation refine depth values, ensuring consistency across views and preserving projective invariance. You can go on to the next slide.
Okay, so the results overview. So the model was applied to reconstruct two iconic structures, which were the Eiffel Tower and the India Gate. Depth maps derived from input images were used to generate detailed 3D reconstructions, and the results highlight the practical application of projective geometry principles in 3D modeling. Next slide, please. Okay, so first is the Eiffel Tower reconstruction. So as we can see over here, this is the input image, and then next to it we can see the depth map, where it pretty accurately estimated it. And as you can see, the lighter the lighter colors represent the closer regions, and the darker colors represent the further regions. And now you can go to the next slide. Okay, so figure 2, which is shown over here, displays the reconstructed 3D model, and the reconstruction accurately preserves the structural features and proportions, demonstrating the framework's ability to handle intricate architectural details. Next slide. Oh, wait. I think this is the wrong image, but we had the image somewhere, like on a different slide. Okay, so similar to the Eiffel Tower, we had a depth map for the India Gate, although the image for some reason wasn't showing. But here's the final 3D reconstruction of it. And the model still preserves the arch structure and the spatial positioning, showcasing how good it is at reconstructing the architectural landmarks. Okay, so the significance and applications. So the results demonstrate the efficiency of a projective geometry-based approach for accurate depth estimation and detailed 3D reconstruction. So potential applications include cultural heritage preservation, which is digitizing and preserving historical monuments, and urban modeling, which could be creating realistic 3D cityscapes, and lastly, virtual reality, which would be enhancing immersive experience with precise 3D environments. Next slide, please. Yep. So conclusion. So projected geometry provides a comprehensive mathematical framework that is essential across various fields, including computer vision, computer graphics, architectural modeling, and more. By accurately handling transformations, projections, and invariance properties, it allows for deep understanding of geometric relationships between images and real-world scenes. Next slide.
Our project demonstrated the power of projective geometry in 3D reconstruction, particularly through depth estimation and model generation, as seen with the Eiffel Tower and India Gate. The success of this approach opens doors for further advancements in depth accuracy, with future applications in augmented reality, robotics, and cultural heritage preservation, where detailed 3D models are essential. Next slide. Thank you.
Yeah, we couldn't have done this without, of course, Shaif, sir. So thank you
Yeah,
so much.
so a big thank you to sir.
Yeah, okay. So that was some impressive work. So two young students showcasing the grasp of a really complex subject. So any question from the audience? So I see a comment by Wikipedia. Okay, then if there are questions, then do feel free to reach out the authors. So the information is given. Okay, then thank you everyone.
Thank you.
Thank you.